You're falling through a wormhole right now. Not literally, but imagine you could. What would you actually see? If you said a swirling tunnel of light, you're thinking like Hollywood. If you said nothing because wormholes are purely speculative, you're thinking like many physicists. But here's what's wild. The physicists who do study wormholes, the ones working out the theoretical math, they've calculated exactly what you might see. And it's nothing like the movies. It's weirder, more beautiful, and completely mind-bending in ways that special effects can't even capture. Let's start with what a wormhole actually is in theory, because the name's misleading. It's not literally a hole you could see with your eyes. It's not a physical tunnel you could point a flashlight down. A wormhole is a hypothetical shortcut through space-time itself. And to understand what that means, you need to think about space completely differently. Here's my favorite way to picture this. You're an ant living on the surface of an apple. To you, that apple's surface is your entire universe. It's all you can perceive. Now, if you want to get from one side of the apple to the other, you've got to crawl all the way around the surface, right? But what if someone took a needle and poked it straight through the apple, creating a tunnel from one side to the other? Suddenly, you could take a shortcut through the apple's interior, even though that interior was completely invisible to you before. That's essentially what a wormhole would be for us. We're three-dimensional beings living in four-dimensional space-time, and a wormhole is a tunnel that connects two distant points in space by cutting through dimensions we can't normally perceive. Instead of traveling the long way through normal space, say 25,000 light-years to the center of our galaxy, you could theoretically step through one end of a wormhole and emerge at the other end almost instantly. Now, the key phrase here is would be. Wormholes are mathematical solutions to Einstein's equations of general relativity, the same equations that perfectly predict how GPS satellites need to adjust their clocks and how light bends around massive objects. The math works beautifully, but the math also requires something that might not exist: exotic matter with negative energy density. Think of it as matter that pushes against the curvature of space-time instead of following it. It's like having a weight that falls upward. Without this bizarre exotic matter propping open the wormhole's throat, gravity would pinch it closed faster than light could travel through it. So we're talking about something that's mathematically possible, but might be physically impossible. So what would you actually see if you approached a wormhole? This is where it gets absolutely fascinating, because physicists have worked this out in extraordinary detail. First, forget those flat, disc-like portals you see in movies. A wormhole would appear roughly spherical. Picture a three-dimensional sphere just hanging there in space. Here's why. Imagine you're looking at a basketball from across the room. You see a circular outline, right? But you're actually seeing a sphere. You just can't perceive the full three-dimensional shape from your single viewpoint. A wormhole works the same way, except it's a four-dimensional object that we can only perceive in 3 dimensions. What we'd see is its three-dimensional shadow, which looks spherical. But this isn't just any sphere. As you get closer, you'd notice something extraordinary. You can see through it. The sphere would act like the most incredible lens in the universe. Light from the space on the other side of the wormhole would travel through it and reach your eyes. So if the wormhole connected Earth to a point near the center of our galaxy, you'd literally see the galactic core appearing inside this spherical region of space, where it definitely shouldn't be. Now here's where it gets really weird. You wouldn't just see a simple window to the other side. The wormhole would create multiple images of everything behind it. Remember, this is a curved tunnel through space-time, and light can take different paths through it. Some light rays would go straight through the center, others would spiral around the throat of the wormhole before emerging. Each path creates a different image at different magnifications, arriving at your eyes at slightly different times. The result? You'd see this complex, layered view that's absolutely nothing like science fiction. The most direct image would appear in the center of the sphere. This is light that took the shortest path through the wormhole. Around this central image, you'd see a series of concentric rings, each showing the same view but smaller and more distorted. These are gravitational lensing effects, created by light that took longer, more curved paths through the wormhole's throat. But wait, there's more. You'd also see your own universe reflected back at you. Light from stars behind you would enter the wormhole, bounce around its curved interior, and come back out the same side. So the outer regions of the wormhole sphere would show a distorted, funhouse mirror version of the space around you. It's like looking into the most complex lens imaginable. Now here's where the simple picture completely breaks down, because wormholes, if they exist, wouldn't be simple or stable at all. First, there's what I call the approach problem. Recent calculations show that wormholes would be incredibly picky about how you enter them. If you approached from the equatorial region, imagine the wormhole as a globe and you're coming in from near the equator, the gravitational tidal forces would be enormous. These forces wouldn't just stretch you, they'd reflect light back out. So if you were looking at the wormhole from the wrong angle, you might not see the other side at all. You'd just see a spherical mirror reflecting your own universe back at you. The safe approach would be from the polar regions, coming in from the top or bottom of the wormhole sphere. From these angles, the tidal forces are manageable, and light can actually make it through the throat. This means the view through a wormhole would change dramatically depending on your viewing angle. From the side, it might look like an opaque sphere. From above or below, it would be your window to another part of the universe. But here's an even bigger complication: time. Wormholes don't just connect different places, they can connect different times. Depending on how the wormhole formed and how its two mouths have moved through space-time, you might be looking not just across space, but across time. The light coming through might show you the other side as it was years, decades, or centuries ago. Or, in some theoretical configurations, you might actually be seeing the future. And then there's the instability problem, which is genuinely mind-boggling. Even with exotic matter holding it open, a wormhole would be incredibly sensitive to disturbance. We're talking about a single photon, literally one particle of light, passing through could potentially destabilize the entire structure. The exotic matter required to keep it open would need to be precisely calibrated. Too little and the wormhole collapses. Too much and it might expand uncontrollably or develop other bizarre properties. Some physicists have calculated that certain types of wormholes might only allow passage in one direction at a time. Try to send something through while something else is coming back, and the whole structure could collapse. Others suggest that the mere act of observing through a wormhole, having light travel through it to reach your eyes, might be enough to destabilize it. You could literally destroy it just by looking at it. Why does any of this matter? After all, we've never seen a wormhole, and we might never see one. But understanding what they would look like if they existed tells us something genuinely profound about the nature of reality itself. First, it reveals just how strange our universe really is. We live in a cosmos where space and time can be bent, twisted, and potentially even torn. The fact that Einstein's equations that perfectly describe the orbit of Mercury and the behavior of atomic clocks, also predict these bizarre tunnels through spacetime, shows us that reality is far weirder than our everyday experience suggests. The universe is under no obligation to make sense to us. Second, it's actually changing how we search for them. Astronomers are now looking for the specific visual signatures that wormholes would create. Those gravitational lensing effects, those multiple images, that spherical appearance, these are all detectable. If wormholes exist naturally in our universe, we might actually find one by recognizing its unique optical fingerprint. We'd know one when we see one. The search isn't just academic curiosity. Some theoretical physicists believe that microscopic wormholes might be constantly forming and dissolving in the quantum foam of spacetime, the seething, bubbling activity that happens at the smallest scales of reality. Others suggest that the mysterious dark matter that makes up most of our universe might be connected to wormhole physics. Understanding wormholes might be key to understanding the fundamental structure of everything. And there's a practical angle too. While we can't create traversable wormholes with current technology, not even close, understanding their physics is pushing the boundaries of what's possible. The exotic matter required to stabilize a wormhole is related to other cutting-edge physics concepts like negative energy, quantum field theory, and the Casimir effect. Research into these areas could lead to breakthroughs in energy generation, propulsion, or even quantum computing. But perhaps most importantly, thinking about wormholes forces us to confront the limits of human perception. We experience the universe as three spatial dimensions plus time, but the math suggests there might be more. Wormholes are potentially our first glimpse into those hidden dimensions, a way to see beyond the boundaries of our normal experience. They're like cracks in reality that let us peek behind the curtain. So what would you see inside a wormhole? Not a swirling tunnel of light, but something far more extraordinary. A spherical window showing multiple layered images of another part of spacetime, surrounded by distorted reflections of your own universe. The view would change dramatically based on your approach angle, might show you different times as well as different places, and would be so unstable that the very act of looking through it could cause it to collapse. It's a vision that's simultaneously more mundane and more magical than science fiction imagines. More mundane because it follows the precise, predictable laws of physics. More magical because those laws allow for shortcuts through the very fabric of reality itself. We may never see a real wormhole, but we know exactly what it would look like, and that knowledge alone reveals just how strange and wonderful our universe really is. Sometimes the most incredible thing about physics isn't what we can build. It's what we can imagine, calculate, and understand, even when it's completely beyond our reach.